So, welcome back. Uh, in the last session, we saw that one of the problems with hill climbing is that it gets stuck in a local optima, a local maxima or a local minima. And as promised, we are going to start looking at algorithms which try to escape from such local optima. In the process, we will also look at this notion of solution space search, and the difference between state space search and solution space search is that in state space every node in the search space was a state and you could move from one state to another, whereas in solution space search every node in the search space is going to be a candidate solution, and essentially we would be searching through candidate solutions looking for a node which is actually a solution, and such a approach is called solution space or plan space search. This is the algorithm that we saw in the last sessions, and this is just to recap that what hill climbing does is that it moves from a given node to the best neighbor if it is better, else it terminates. And we have observed that we do not need to do sorting, we can just simply pick the best neighbor, and we had also observed that the termination criteria has changed, and it is a local algorithm, which means that it has burnt its bridges from all the nodes that it had generated earlier essentially. And we had made this observation that it is a constant space algorithm, which is good, and that it will terminate also reasonably fast, because it just goes up the gradient and stops when the gradient becomes 0, and that is a termination criteria, that it stops when the termination is gradient has become 0, and in that sense we are treating it as an optimization problem. However, it is not complete, because it often gets stuck on a local optima, and this is a figure that we had seen of you thinking that you have reached an optima, in this case a maximum, and finding that it is not the global, but only a local maximum essentially. And this is an example that we had seen in the state space, where we saw that the surface that the algorithm is traversing over is not monotonic, and therefore, there is a possibility of getting stuck at a local minima in this case. And we had said that given that we cannot change the heuristic function, we will look at that approach also a little bit later, but the alternative is to look for algorithms that can do better than hill climbing, and we had promised to look at deterministic methods, and that is what we will start off by doing in this session. Okay, so, what is the solution space or the plan space? Let us begin by looking at that, and we will look at this famous SAT or satisfiability problem, in which this comes naturally. So, observe that we have talked about SAT earlier, and we had classified it as a configuration problem, in the sense that we are looking for a particular node which is the solution, and we are not really looking at a path of going from some given start node to the goal node. So, we are only interested in a node which satisfies certain properties, and SAT is a typical example of that essentially. Okay, so, just to give a quick definition, given a Boolean formula is made up of variables which can take values 0 or 1, made up of a set of propositional variables, we will call them A, B, C, D, E, each of which can take a value of 0 or 1 or false and true, as the case may be. Both are equivalent, we often treat 0 as false and 1 as true. So, we want to look for an assignment for the variable such that the given formula evaluates to true or to 1 essentially. So, that is a satisfiability problem. It is a very famous problem. We will spend a little bit of time on this, and it is very interesting, because it was shown to be one of the harder problems by Gary and Johnson in 1983, I think, and they showed that the SAT problem can be used to define a complexity class of problems, which we now call as NP complete set, and this is the canonical problem in the NP complete set. We will come back to this later again. So, here is a small example of a formula on the variables a, b, c, d and e. So, we have a or not e, and then we have e or not c implies not c or not d. And what you see are the other things are the logical connectives. So, the or and the and the implication sign and the negation sign essentially. Now, this formula can be made true by the assignment a is equal to true, c is equal to true, d is equal to false and e is equal to false amongst other assignments essentially. Very often we work with SAT in the conjunctive normal form, which is the CNF form, and the CNF form is a set of clauses which I am underlining now, and the clauses are joined together by the AND connective as shown here. Within each clause we have the OR connector, and so each clause is a disjunct of some expressions, and each expression is either the proposition or the negation of a proposition. So, in this CNF form the negation sign is pushed innermost, and those of you who have studied logic or Boolean circuits, you know that we can always convert any formula into a CNF form, and very often when doing experiments we tend to work with CNF forms essentially. It may be also interesting to note that when you convert a formula into a CNF formula, very often you grow the size of the formula, sometimes exponentially, and after that we have to talk about the complexity of the algorithms. So, in solution space what we do is that you work with methods which are called perturbative methods, which means you look at a candidate solution and perturb the solution a little bit. So, the solution space is a space of candidate solutions. A local search method generates the neighbors of a candidate by applying some perturbation to the given candidate. So, our moveGen function now becomes a neighborhood function, that what can you do to change the candidate a little bit essentially. And a lot of what we will do in the next couple of weeks is going to look at this neighborhood function, which says that you take a candidate and change it in some way and hope that that leads you to a solution candidate essentially. Now, if you look at the SAT problem, if you have n variables, then you will have 2 raised to n different candidates, because for each of those variables you can give a value of 0 or 1, and there are n variables. So, the number of candidates is 2 raised to n, which is quite a large number. We will kind of try to get a sense of this large number a little bit later again, but just imagine that if you have 100 variables, then you have 2 raised to 100 possible candidates, which is a significant number. Now, each candidate is a n bit string, because there are n variables and you want to either give a value of 1 or 0. So, what you see here is an example of a candidate which has got 7 bits, and therefore, this is a problem with 7 variables. And what we are saying in this candidate is that the first variable is 1, the second variable is 0, the third variable is 1, the fourth variable is 1, the fifth one is 0, the sixth one is 1, and the last one is 0 essentially. So, what do we mean by perturbation? What is the kind of change we can make? So, one of the things we can do is to say that you can change one bit to generate a new candidate. Either you can change the first bit or the second bit or the third bit or the fourth bit and so on. And therefore, we have a set of 7 neighbors for this particular example, and what you see in red in each of those candidates is the bit that has been changed coming from the given candidate. Observe of course, that this is a reversible process, that you could have gone back from this to the first one, but since we are doing hill climbing, we will not be interested in going back, because you can only want to go back to moves which are to states which are better, or to candidates which are better than the current candidate. So, one thing that you could do is to look at more than one option at each level. Now, why did we move to hill climbing? We moved to hill climbing to save on space essentially. We said that we cannot afford to have exponential space and exponential time algorithms, which was best first search for example. And we said that hill climbing is very nice because it takes a constant amount of space essentially. But nowadays, given that memory is becoming cheaper and it is available in abundance, we can generalize from there and say that instead of keeping only one best candidate, why not look at B best option. So, we define the term called beam width B and we look at B best options at every stage. So, the search tree would look at something like this. So, here we have assumed that the beam search is 2 and as at each level as we go down, we have taken the best 2 nodes and generated their children. Then amongst all the children that are generated, we again take the best 2 nodes and so on. So, you can try and think of it as a beam being shown through the exponentially growing search space and or a beam which is kind of like a pillar in the search space, and the algorithm has a better chance of finding a solution. As I said, all this makes more sense because computer memory is becoming cheaper and cheaper and you can afford to keep more candidates in the fray essentially. Observe that the complexity of the algorithm is still constant times, except that if you are got a beam width B and the branching factor is let us say k, then you would be generating B into k candidates at every stage, but it is still a constant number. So, here is an example of beam search for the SAT problem that we were looking at. We need to define a heuristic function, and one advantage of working with the CNF form is that we can define a heuristic function which says simply count the number of clauses that are satisfied. So, as you can see in this example, there are 3, 4, 5, 6 clauses. So, the heuristic value can go from 0 to 6 essentially. And remember that this also we are viewing it as an optimization problem, because in the solution all 6 clauses should be satisfied and only then the formula will become true. There are variations of this heuristic function. For example, you could multiply, do a weighted sum of the clauses, because some clauses have one proposition inside, some have 2 and so on. So, you could weight it by the size of each clause as well essentially. But here this search algorithm shows that if you started with the candidate solution where each of the 5 variables A, B, C, D, E is 1, then that has a heuristic value of 3, as you can see here, and then you generate the 5 children and compute the heuristic values, and the nodes shown in blue are the best 2 children, they have heuristic value of 4. Then you generate all the children of all those 2 nodes and you get 10 children, and then you move to the next 2 which are heuristic value of 5. So, you can see that like hill climbing, as you go down deeper into the search tree, the heuristic value is improving essentially. You started with a value of 3, at the next level we had a value 4, and at the third level we had a value 5. But at this stage, when you take the best 2 candidates which are value 5 again shown in blue and generate all their children, you can see that all the children have either a value of 4 or 5 essentially, which means that none of them is actually better than that. And like hill climbing, the beam search, which is basically, you can think of it as parallel hill climbing with multiple nodes being in contention, will come to a halt because it has reached a local maxima again. Now, there is a node here with a heuristic value of 3, and if you just try it yourself, you will see that moving from this node in a matter of 3 steps, you would actually go to the goal node. But beam search is not able to find this because it thinks that those other nodes are better, the nodes which have heuristic value of 5, but they are in fact local maxima where the algorithm gets stuck essentially. Why did we choose the neighborhood function or the perturbation function which said that change one bit? Now, this neighborhood function that we saw has been shown here in blue, that you are going up from this state which is change one bit, and we saw that it had 5 neighbors. We could have changed, we could have said change 2 bits, and that is the neighborhood function that you see in red, and you can see that if you do that, then you have 5 C 2 neighbors. In this case, we have 10 neighbors, and therefore, it is a different function. And you can also, if you look at the 2 sets of neighbors, the neighbors generated by n 1 function which says change 1 bit, or by the n 2 function which says change 2 bits, then they are actually a disjoint set essentially, they generate different neighbors. So, there is also the possibility of saying that you can change 1 or 2 bits, and that we have here mentioned as a neighborhood function n 1 2, which says that you can change either 1 bit or 2 bits. So, the neighbors will be the union of the neighbors of the neighborhood function n 1 and n 2. So, in that manner we can keep increasing, we can say 2 bits or 3 bits or 1 to 3 bits and so on and so forth. So, we can devise more and more dense neighborhood functions. So, what do we mean by dense neighborhood functions? That these are neighborhood functions which have more number of neighbors essentially, and the most dense being what we can call as n 1 n, which means you can change any number of bits. You can change 1 bit or 2 bits or 3 bits or 4 bits up to n number of bits. You should probably think about, is that a good idea or is that not a good idea? We will see that in a moment. So, n 1 n stands for changing any of 1 to n bits essentially. Now, the first thing you will observe is that generates a graph where every node is reachable from every other node in exactly one step essentially. So, it is like a very densely connected graph essentially. What is the effect of density on the performance of hill climbing essentially? Now, if you recall what the algorithm says, hill climbing says, is that inspect all the neighbors and move to the best neighbor if it is better than the current node essentially. Now, hill climbing gets stuck on a local optimum when none of the neighbors is better than the current node, that we have seen essentially. So, it might seem that it is a good idea to have denser neighborhood functions, because the denser the neighborhood, the less likely that it will get stuck on a local optima essentially. But there is a catch, that if you have a denser neighborhood function, then you need more computation to generate all the neighbor. So, the denser the neighborhood is, the more the number of neighbors that has to be inspected at each step essentially. So, that is a trade off essentially, how many neighbors you will generate and how many would you inspect. Now, this function that we talked about in the just now, which we called as n 1 n, this has 2 raised to n neighbors, which means every possible candidate is a neighbor. And if you are going to inspect 2 raised to n neighbors, then it is like doing brute force search. So, obviously, we cannot afford to do that, and we said that if n is 100, then 2 raised to 100 neighbors is not something that we would want our machine to spend time in. Just try to compute how long that will take to do. So, instead what we do is we adopt a algorithm called variable neighborhood descent, often abbreviated as VND, and this assumes that the move gen function or the neighborhood function can be passed as a parameter to the search hill climbing algorithm. Many programming languages do allow functions to be passed and they treat functions as first class objects, and you can pick one of those languages, especially many functional programming languages, they allow you to do that. So, we will assume that there are some n move gen functions and they are sorted in the order of increasing density. What this algorithm says is that you look at the first move gen functions I. So, we assume that we have things like, let us use mg for this. So, mg1 is the most sparse function, then mg2, mg stands for move gen is the next, and so on essentially. What this algorithm says is that start with I is equal to 1, take the most sparse function and simply do hill climbing. So, what happens with that? It's a sparse function. So, you can generate the neighbors very quickly and you rapidly climb the hill. At some point you get stuck on a local maxima, and that time you change the move gen function. So, just imagine that if you are doing this SAT problem, we had n1. So, first you use n1, then when you get stuck you move to n2, then if you get stuck then you move to n3 or something like that. And so, what you do is that first you use the most sparse function, then the denser function, then the denser function, and so on, and keep doing that till the computation power allows you to do that. Obviously, we can't do a brute force SAT because it is a very large problem essentially. The hope is that most of the climbing or descending, as the case may be, will be done by the sparse neighborhood functions, and eventually very little work will be done by the denser functions.